Good morning, afternoon, or evening, everyone, and welcome to our presentation. First of all, let me thank you all for coming here today. I am Tim from University of California, Riverside. Today, I am going to present about our project, a learn query optimizer for spatial joy, co-authored with Umberto Bellucci, Sara Minorini from University of Verona, Italy, and Ahmed Endoy from UC Riverside. It would be great if you can see some potential ideas to improve the performance of your spatial data system after this talk. First, you may recognize that big spatial datasets appear everywhere, from transportation data, satellite data, medical image, social network data. They are demand to develop efficient spatial processing techniques in research community to process this huge amount of data, especially extract the data insight from the relationship of multiple datasets. Due to these demands, spatial joy plays an important role in many data analysis tasks. Let's take a look at an example as shown in the slides. Given two datasets, one represents the county boundaries of New York, the other contains the nursing home location in New York. Spatial joy can help us to find the total nursing home capacity for each county. Another example of spatial joy is that it can help the health official to understand the spatial dynamics of at-risk populations, then make the suitable response such as health infrastructure improvements, emergency funding allocation, or preventative measures. So what is spatial joy? Spatial joy is a core operation in many GIS softwares and important applications. It allows users to discover data insight from multiple datasets using spatial relationship as a joy key. However, spatial joy is also one of the most resource-demanding operations in spatial database. There are a lot of research efforts to make spatial joy working better, especially in big data era, when the traditional optimization methods are not applicable. In particular, most spatial joy algorithms in big data systems have been implemented with MapReduce programming model. In this project, we consider four most popular algorithms: block nested loop joy (BNLJ), partition-based spatial merge joy (PBSM), distributed index-based joy (DJ), and repartition joy (REPJ). Assume that we have to join two spatial datasets, DI and DJ. Block nested loop joy divides the input into several splits with fixed size, which normally are blocks of 128 MB in Hadoop distributed file system. Then it cross products the two sets of splits to get the final results. Do you think that this algorithm is too naive and not effective? We will discuss about it soon. The second algorithm is partition-based spatial merge joy. PBSM splits both input datasets using a common grid. Then it finds the joy results from all pairs of splits with the same cell in the grid. Is it better than the previous BNLJ algorithm thanks to its smart strategy? We will also discuss about it soon. The distributed index-based joy indexes each input dataset separately. Then it only runs the joy algorithm on the splits which overlap to each other. This strategy helps us to avoid unnecessary computation for the splits which are not overlapping. The last joy algorithm we consider is repartition joy. Repartition joy splits the second dataset using the index of the first dataset, then it joins the pairs of splits which are in the same cell. Assume that you are trying to run spatial joy on your datasets. The main challenge here is we don't know how to choose a suitable algorithm to run your queries as fast as possible. We carry an experiment as follows. Given 1023 pairs of datasets with various size and distribution, we run all four algorithms on BIS and log the running time. BIS is a Spark-based spatial data system. There are no one-size-fits-all algorithms. For example, the simple approach like BNLJ still is a winner in 25.3% of the queries. Why? There are several factors that impact to the joy performance: input size, distribution, number of intermediate tasks. It's even more difficult for non-technical users who do not know how spatial joy internally works in big data platforms. As we can see, there are a lot of challenges of query optimization for spatial joy. The theoretical cost model for traditional spatial joy are not applicable for MapReduce-based algorithms. In big data context, a spatial joy algorithm might need to balance the computation across machines, reduce disk access from distributed file system, or minimize the network overhead. In this slide, we review the research efforts that have been trying to address the optimization problem for join query. For long spatial join queries, there are a bunch of methods which apply both cost-based, rule-based, and machine learning approach to improve join performance. However, there lack a machine learning approach to address the optimization problem for spatial join, while the traditional approach do not work well in big data context. Motivated by these issues, we propose SJML, a learned query optimizer for spatial join in big data platforms. SJML provides different levels of cost estimation which are useful for existing database systems. In level 1, spatial join cardinality estimation, it predicts the result size of join queries, which is algorithm independence metric. In level 2, ambient test estimation, it predicts the number of geometric comparison operations, which is an algorithm-specific and hardware-independent metric. Finally, in level 3, algorithm selection models, it predicts the best join algorithm in terms of running time. SJML includes two phases. Phase 1 is the training phase. First, we use a data generator to generate a lot of join datasets in different distributions. Second, we use a feature extraction component to compute the data summarized. We will discuss detailed features in the next slides. Next, we execute the for join algorithm on the input datasets. After that, we will know the best join algorithm in terms of running time for the given input datasets. Finally, we fit the feature X of data summarized and label Y of best join algorithm to a random forest classification models. The trained models will be used in phase 2 applications. Whenever we need to join two datasets, we will use a feature extractor to compute its features, put that feature to the trained model. The model will suggest the most suitable join algorithm for the given datasets. After that, the system will execute the join queries using the structured algorithm. Let's visit the feature extractor components in the proposed system. This step extracts a set of standard features for each pair of datasets to prepare the data point for model trainings. We extract features in different groups: statistical-based features, input relationship features, histogram-based features, and partitioning-based features. We would recommend you to read our paper for the detail of each feature. We combine different groups of features to observe the impact of each group to the accuracy of prediction models. In particular, we have three different feature sets. Feature set 1 contains the statistical-based features. Feature set 2 adds histogram-based and input relationship features. Feature set 3 adds the partitioning-based features. To evaluate the performance of different models, we use three metrics: mean absolute errors, mean absolute percentage errors, in which lower is better, and accuracy, in which higher is better. To train the models, we first need to prepare the training datasets. We use both synthetic and real datasets for our training purpose. Synthetic data are flexible in size, with popular data distribution, and you can generate as much data you want. We utilize Spiders, a web-based spatial data generator, to generate our synthetic datasets. Real data is also very important because it makes sure that our model can work well in real scenario. We use OpenStreetMap dataset as the real data. Finally, we combine both of them to prepare our training data. You can imagine that this is similar to the process of produce synthetic blend car oil. In the next section, we will discuss about the experimental results. First, we train and test the join cardinality estimation models. The baseline B1 comes from a paper of Walid Aref on GIS 94, which computes the spatial join cardinalities based on feature set 1. We train and test our data in about 7,000 data points on a random forest regression model M1 with the feature sets 1 and 2. We don't apply feature set 3 since the partitioning-based feature do not affect join cardinalities. The results show that M1 is much better than baseline B1. More important is the machine learning-based models is flexible to accommodate different sets of features. For the level 2, we use separate models to predict the number of ambient tests for different join algorithms. The baseline we use is theoretical models proposed in a paper in Geoinformatica 20s. The results show that the random forest regression model can predict the number of ambient tests very well, while the baseline methods cannot give us a reasonable accuracy. Finally, we build the algorithm selection model by feed the training and test data to a random forest classification models. We compare it with two baselines. Baseline B31 implemented from a paper on 6 April 2017. Baseline B32 from a paper on Geoinformatica 2020. The results show that the proposed model M3 could predict the best join algorithm with a reasonable accuracy and no errors. Overall, the proposed spatial join cost estimation model in different levels could be a great component to help people who want to speed up their spatial join queries. I hope this presentation is convincing enough for you to think about integrating SJMLs in your current spatial data system. It should be very simple and smooth for you. We share the data, code, and pre-trained model on GitHub. The pre-trained algorithms and hardware-independent models like M1 and M2 can be used out of the box. If you would like to use the hardware-dependent models M3, you might need to retrain the model with your configurations. In conclusion, we propose the first machine learning-based query optimizer for spatial join in big data platform. SJMLs can choose the best algorithm to run, estimate the join kinetics or number of ambient tests for a specific algorithm. SJMLs can be trained using small medium datasets and estimate performance of spatial join on large datasets. In the future, we are planning to discover deep learning-based approach to avoid the feature selection process. Thank you for your attention. We look forward to your questions.